Hello, everyone. I hope you're doing well. Real quick announcement. If you're watching this on Friday or over the weekend, we will be back, quote unquote, in seat on Monday. So back in the classroom, my quarantine will finally be done. Today, what we want to look at is section 1.7, which is more about derivatives. And then we'll also look at 2.1. In the section 1.7, more about derivatives, one of the first concepts we come across is differentiating with something with respect to something besides x. The default we will tend to use is the independent variable being x and the dependent variable being y. But there's nothing saying that we couldn't just relabel these and call them something different. So for instance, if we had this function here, where s is a function of p, what we might try to do is find the change in s over the change in p. Whatever we're taking the derivative with respect to, that's our independent variable. So that will be p. And our dependent variable in this case will be s. We can let p take a variety of different values, but s will depend on what the values of p are chosen to be. And if it helps to see lined up with more familiar xy notation, here we have just what we've written above, here and here. But now what we've done is written the exact same thing with color coding so that all the s's have been replaced with y's. All the p's have been replaced with x's. Oftentimes it'll be useful to write an equation where the independent variable is not x. For instance, if you had a function based on time, to kind of remind yourself that, you might say that f is a function of t for time. And there's many, many examples of this in the sciences. X just tends to be the default. Now, besides finding derivatives with different independent and dependent variable, we can also find higher order derivatives. We only will start calling it now the zeroth derivative, though it was kind of this all along. The zeroth derivative is essentially don't take a derivative. So if you just leave the function as it is at f, that's what we would call the zeroth derivative. The first derivative is what we've been thinking of as the derivative. As we're going to see, or you can already see, there are many different derivatives, each of a higher order. But the very first one we learned is the first derivative. This is notated in prime notation as f prime of x, or in Leibniz notation as d dx f of x. Now, hopefully there's a clear pattern how to notate the higher derivatives. So if we took the second derivative, that would be f double prime instead of a single prime twice. And then if we use Leibniz notation, it would look, well, in one case, it could look like this, where you have the first derivative and you're taking the derivative of that. One reason I like Leibniz notation is it's a little more descriptive of what's happening here. So we have the derivative, which is just this here, and then we take the derivative of that thing to get the second derivative. Every time you find a higher order derivative, you obtain it by taking the derivative of the last derivative. So to get to the first derivative, you take the derivative of f of x. Actually, let me color this like so. Maybe this will help. Even better. Let me try this. So we'll build it off to the left. Oh, I kind of like that better. And let me add a little bit more. Okay. Yeah, I kind of like this. So with the zeroth derivative, what you do is you start with just the function itself, nothing fancy. Then the first derivative, you take the derivative of the previous thing, which was just the function. For the second derivative, you take the derivative of the last thing. So I've tried to set this up so that it's maybe more visually suggestive. If you wanted to take the third derivative, you might have guessed it, you take the second derivative and you differentiate that thing. So notice that I just copied and pasted the second derivative. I'll put brackets around it. And then let's use green maybe. Say ddx. So to find higher order derivatives, you just take the derivative over and over and over again. All right. If we want to find higher order derivatives, let's say as functions, and thinking back for a second, you can compute derivatives in one of two ways, either as a function or as a value. If you compute it as a value, that's the slope of the tangent line to the function. At the given point. So it gives you a geometric quantity. If you're computing derivative functions, that will allow you to find the slope of the tangent line at any given point in the domain. But it's a little more general, of course, because you're kind of doing it simultaneously for all values. So let's say we want to compute the derivative, excuse me, of x cubed plus 7x, supposing that's f of x. If we take the first derivative, so let me maybe do some work up here. Taking the derivative of this x cubed plus 7x. If it's not immediately clear in a geometric sense what's happening with this thing, it's usually a good idea to use the derivative rules. And we haven't talked about all the derivative rules yet. There will be more, but certainly we have some to work with right now. One such rule is the rule that you can take the derivative over a sum or difference. So we can take the derivative of x cubed and then add to it whatever the derivative of 7x is. So that's by, I don't remember the names exactly, but it's going to be something like the sum rule. Then we can actually use a rule right away on this term. We can use namely the power rule. The power rule tells us that we get 3x squared. And depending how you want to look at 7x, you could think of it as just a line through the origin with slope 7, obviously. So you can just see that it's going to have a tangent line with slope 7 no matter what. Or you can use some of the rules, some of the algebraic rules, namely the constant multiple rule, and then the rule that the derivative of x with respect to x is 1. So you have some options there. But certainly, no matter what, we had to use the power rule. There was no getting around that. So I'll just put ... other rules. Or geometric intuition. All right. We computed the first derivative. It's 3x squared plus 7. Now to compute the second derivative, we need to know what the first derivative is, but we just computed that. Actually, we will do that in a second, but let me take a step back. let's say at this point you wanted to know what the third derivative is. And the answer is you could not. You need to know what the last order derivative is. If you want to compute the fourth derivative, you need to know what the third is. That's it. Just whatever the last one is. So if there's a hole somewhere, it can cause, complications in your computations. All right, with that said, let us now do the derivative of the derivative, which is the second derivative. In other words, f double prime. So if we compute the derivative of this, I'll just say by the different rules, what we end up with is 6x. Do it one more time to get f triple prime. And in that case, we'll just get 6. Finally, for the work we're doing here at least, if we want to compute the fourth derivative, once you start getting to enough primes, namely 4, where it kind of just becomes unwieldy mess, we can switch to this notation. We put a pair of parentheses in the exponent spot, and then we put the number of derivative. So if it's the second derivative, it would get a 2. If it's the 20th derivative, it would get a 20. In this case, we're looking at the fourth derivative, so that's why I'm putting a little 4 here. In parentheses, that's critical. Without the in parentheses, it'll just look like a multiplication of the function over and over, like the function to the fourth power. So no, this is the fourth derivative. If we compute the slope of the tangent line to this curve, a constant function, that slope will always be 0. All right. Next. So how would we find higher order derivatives as values? Well, we actually just take what we looked at on the previous page and we essentially add a step. So if we want to find the first derivative evaluated at a, we first can compute the general function for the derivative values and then substitute in a particular number, x is equal to a. That will then tell you exactly what this is. Same thing with the second derivative. And let me give it some reorganizing like we just saw. I want to try to get everything lined up. And something like that. And of course, this would extend infinitely to the left if we just kept computing derivatives. But hopefully, in this finite case, it gives you an idea. Alrighty. Now, suppose that what we want to find are the derivatives to this function when we're at the value x is equal to 1. So we'll use, in this notation, the same a value. But like we've highlighted here, that's what we're going to be substituting in. So if we take f of 1, for instance, that is simply the function f of x evaluated at x is equal to 1. That's all that means. In particular, what we get when we substitute in x is equal to 1 into this function, I think we get 2 plus 5, so 7. Now at the same value, x value, we're asked to find the first derivative there. Since our x or a value is equal to 1 and we're computing the first derivative, what we do is we first find the first derivative function, and then we do this substitution or evaluation. Maybe I'll keep that in yellow just to kind of see that it's the same in every place that we do this. All right, the second derivative is simply going to be the second derivative function, but you may have guessed it. It's going to be that function evaluated at x is equal to 1. Then for f triple prime, same kind of thing. We're going to take, and now I'm going to condense notation. So I'll take d cubed dx cubed f of x. That's just a shorthand notation for taking the derivative 3 times of f of x. So we'll take that and then we will evaluate it when x is equal to 1. Finally, the fourth derivative at 1 is going to be equal to, and I'll use the same notation as the third derivative, d to the fourth, dx to the fourth, f of x. And that's just the function itself, but we want an actual value. So in order to get that, we will evaluate at our x is equal to 1. All right. Now, another topic that we mentioned a little bit earlier, but is certainly good to come back to, it's kind of the prototypical business application, if you will, looking at marginal cost, later marginal revenue, marginal profit. And when you hear marginal cost or marginal whatever, and you hear revenue, profit, and all this, it's really not too crazy what's happening. So the marginal cost is just a fancy name for something we already know. In particular, if you have c of x is a cost function, then we would say c prime of x, which is the first derivative of c with respect to x. We would call this the marginal cost function. Now, I don't know that I really love the term marginal. I might have preferred something like projection cost function or prediction or something like this. The reason being, let's say that you are producing a number of units of something, and you know that cost happens to be whatever. Let's say it happens to be here, and it's, if that was A, let's do B here. It's some value, but you exactly know what it is because at that moment you are producing A units. So that's known information. Then information that you might like is to know, well, if we increase production, what's going to be the additional cost? Do we increase production, make one more unit a day or whatever amount of time, and it adds like negligible cost? Or is it that if we add another thing, it'll add a lot of cost? So the reason I like the terms projection and prediction is because they give more of an intuitive sense of what's happening. You use this, what'll be a tangent line, but the marginal cost function, you use that to predict what the value might be when you increase production or, do whatever. In reality, it might be that your cost, it goes to here if you produce one more thing beyond A. And it could be that the marginal cost function here, let's say, what do I want to say? Gives you a value that's, let's say, a little bit of an overshoot of what the actual one is. the way to, actually, no, I want to take that back. I'm not going to finish that thought. Right. So the marginal cost, the marginal revenue, marginal profit, they're all using the derivative where you have a slope of a tangent line and using them to predict what the next value would be. The reason you might use that is because it's kind of easy to construct a tangent line. Once you're in practice, if you haven't done it for a while, it could maybe definitely give you trouble, but once you're in practice, it goes pretty quick. All right. So let's say, as a little bit more specific example, we've got 50 units and the cost of producing 50 units happens to be $6,000, so $6 million. Now, what you would like to know is how much will it be to produce 51 items instead? And you would ask this because it may just happen to be that for whatever reason, that if you produce one more unit per, I don't know, per year or per month or per whatever time cycle, if you produce one more, maybe it will increase the cost by a ton. Or maybe the cost will hardly increase at all. So there's a variety of things that could happen. This marginal revenue function gives us a way to quickly find tangent line slopes. And then that lets us kind of track what we might predict the new cost to be. Let me jump over the next page. Right. Okay, I want to say one more thing here. So notice that there's just a tangent line or just a line that happens to, actually, let me bring this back. I'm going to make this a little interactive. I guess not interactive, but dynamic. Let me get rid of this. Nope, that was not what I wanted. Get rid of this. And let me get rid of this dot. Maybe just easier to redraw it. Okay, good. Now, suppose you know two things. You know that when you're producing 50 units, the cost is going to be 6,000 or 6 million. Then you have some other information, namely, you know the marginal cost, let's say. And again, when you think marginal, or at least what I think, is predictive. So it helps us predict what the next cost or the next profit or the next revenue should be. So what we do, and I had this already set up, but kind of going back to fundamentally what happens, is we say, well, when we're at 50, we're at 6,000. So when we're at 51, what should we be at? Well, that will depend on the slope of the marginal, what do I want to call it? The marginal tangent line, I guess. So it will depend on the slope of this line that you come up with, which comes from the marginal cost function, which is just the derivative. So you'd follow along this thing until you get to above 51, and then you continue to follow up, and that gives you a new point. Now, this is not necessarily on the curve. I can quickly draw a couple curves that totally missed that point. That could be one. Another one could be like this. So notice the one that's on the marginal tangent line, if you will, notice that it can be kind of far away from what these actual curves would look like. So it's just an approximation. And the closer you are to the closer you try to approximate values for, closer to your kind of base value, in this case would be 50, the more accurate you're going to be. You kind of notice that there's something like a squeezing going on in this area, here and here. So there's lots of room between these two curves, but then they kind of squeeze together like this. All right. So this more or less concludes 1.7, section 1.7. Now let's look at section 2.1. So with section 2.1, the idea is to describe graphs either by coming up with the information for f prime and f double prime, or one could potentially have the information for f prime and f double prime, and then work backwards to find f. So using partial information to find other common functions in their graphs. So we'll consider f. I'll try to color code that as in cyan when possible. We've got green. I'll try to color code that as f prime, or the tangent line at a point. Try to do that whenever possible. And then finally, we've got f double prime. Now we'll notice this slide. I'm going to jump to the next slide. Notice it's pretty similar. The difference being the first slide has to deal with f prime, first derivative, and the second line has to deal with the second derivative. But these, just these two derivatives tell you quite a bit about a graph. Like you can get very accurate with a graph just using f prime and f double prime. And here's how. So if you look on an interval, let's say a to b, and every value in that interval, when it's plugged in to f prime, if it gives you something greater than 0, we would say over that interval, the function is increasing. And if we think about it geometrically, it makes total sense. If f prime of x is greater than 0 for x in this interval, then that means for whatever value in the interval, when you substitute it in to f prime, you get a positive number. And that means your slope is going to be positive. So f prime is exactly the slope of the tangent line. I should say, that's not completely true. I should say f prime, oops, f prime at, let's see, what should we use? How about C? Actually, no, never mind. I will withhold going down that route for now. No, it's good. Okay, so f prime of C is exactly the slope of the tangent line to f at C. These are one and the same thing. And hopefully I've repeated this enough, and I'll continue to repeat it to where it kind of becomes second nature to you. And if someone asks you on the street, hey, what is the derivative? Like, oh, I got you, fam. If you're looking for it in terms of a value, it's the slope of the tangent line to the curve at a given point. And if you're looking at it as a function, then there's various ways to compute it. But when you're trying to find a value, it is the slope of the tangent line to the function at the given value. So when we're looking at these various x values in this interval, we're saying the slope of the tangent line there is positive. I'm going to zoom in. So if we look here, I've drawn a few example tangent line slopes, and we can see that they're all positive. Now, some may be more positive than others. For instance, I think the most positive one is probably this one, but certainly this one is not. Sorry, this one is less positive than this. But the important thing is they're all positive. So each one of them is sort of working to push the graph upward as you move to the right. Jumping down to the bottom for a second, the very opposite case holds when f prime is less than 0. What that means is that the slopes of the tangent lines to that curve, they would be negative. So they have downward slopes. If we zoom in to something like this, we have a negative slope, a negative slope, a negative slope, a negative slope. What these tangent line slopes do is they work to push the function downward as you move to the right. And if we have a case where f prime of x is greater than 0, f prime of x is less than 0, there's the case in the middle when f prime of x is equal to 0. Now notice we don't say that exactly. We don't have f prime equal to 0 here, because f prime being equal to 0 doesn't guarantee what we're about to talk about. What we're about to talk about here. Seems grammatically correct, but having those two abouts also seems redundant. Anyways, so this thing here, and there'll be an analog for the second derivative. This says if f changes from increasing to decreasing, or the other way, if it goes decreasing then increasing, and that change happens at a given x value, let's say c, then what we would say is the point, just c and f of c, that gives us the x and the y value. So that's that point there. We say that is a critical point of f. Now, the important thing is just to note that it's where we go from increasing to decreasing or decreasing to increasing. We could have called it a variety of things, but it happened to be that the current standard is to call it a critical point. Now, take all this and we'll have a direct analog for the second derivative. So in the first derivative, we looked, where was it positive? Then we looked, where was it negative? And then we said, if there's a spot where it changes from this thing to this thing, that kind of spot in the middle, we'll denote that somehow. So if we go from increasing, going upward as we go to the right, to decreasing, going downward. So we go up, then we go down. That spot where there's the changeover, we're going up, 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 up. Then we kind of right over C, we stop. And then it changes from having gone upward to now going downward. So C in this case would be a critical point, or C, f of C would be a critical point of f. And also note that this must be the case where we have a 0 slope here. I'm not claiming that's obvious, but I am making a claim that you can trust is true for now. So we have 0 slopes there. Now take all this, do the same thing, but for the second derivative. When the second derivative is positive, we say that f is concave up. Now what that means is that the first derivative is increasing. Okay, so what's up with that? Well, the derivative as a value can be given by looking at the slope of the tangent line to the curve at that point. So let's say close to A, we use a value to compute the slope of the tangent line there, or the first derivative, saying the same thing. And what we get is this slope. Now it looks very negative. I don't know what exactly, maybe negative 10 or something. Doesn't really matter. But it's something that's a pretty big negative number / negative slope. Because f is concave up, what should happen when you're concave up is you should go from a really negative slope to a less negative slope and less and so on. And eventually, if you just go from a very negative number and keep increasing it, depending on what you're increasing it by, I mean, get into some weird things with infinity, but as long as you steadily increase it, the slopes are eventually can go from negative to positive. They don't have to. They could start negative and stay negative, but the kind of classic shape that you get is this so-called bowl shape. So it looks kind of something like this. On the bottom, kind of flipping a lot of this again, if f double prime is less than 0, if it's negative, then we say that f is concave down. Now run the exact argument we just looked at up here. But now what we do is we start at whatever. You don't have to start with a positive slope. That's not necessary. But what is necessary is that as you move to the right, if you're concave down, your slopes will decrease. So notice we have this, positive slope at whatever value. Then we have still a positive slope, but lesser value, or closer to 0, I guess, if you will. Then we have a 0 slope that's certainly less than a positive number. And then it keeps decreasing, so then it goes into the negatives. And that fact is what gives it the bowl shape here. Now you can have sort of partial, this is sort of a partial bowl shape, I guess, if you will. Like it doesn't have to be an honest to goodness kind of bowl looking thing. It could be like this. This is all concave down. Even, it's not a bowl in the sense of like being able to hold something. But it gives you the general idea. Now, like in the case of f prime, we looked at increasing and decreasing. These were the two types of behaviors that the first derivative would tell you about a graph. Where does it increase? Where does it decrease? And then there was a point kind of between the increase and decrease that we call the critical point. Now what we'll do here with the second derivative is we will look at an inflection point. So when you do either one of two things, you go from concave, whoops, didn't want that one. When you go from concave down to concave up, or vice versa, if you would be at concave up and then go to concave down, just as long as you switch concavity, that spot at which you switch, you take the x value and then plug it into the function to get the y value. And that point is called the inflection point. So this point here, maybe I'll put it another color to kind of signify they go together. There we go. So that spot where there's a change. And now this may seem like a lot to remember, but you can kind of simplify some of this. For example, the first derivative and the second derivative have a similar structure where when either one is positive on an interval, you get some specific behavior. When either one is negative on an interval, you get some other specific behavior. And they're very much related, both the behaviors. So if you remember concave up ever, the kind of next thing that would go with that is concave down. Or if you think about increasing, the next thing that should go with it is decreasing. Both of these have the cases of F prime or F double prime being positive and what happens, or negative and what happens. And then they have something in the middle for the changeover between the two things. One happens to be slopes of tangent lines, and the other one happens to be the kind of, I don't really want to use the word curvature because that has official mathematical meaning, but how curvy they are, I guess, whether you're curved up or curved down. Alrighty. Along with this, and we'll do some examples soon, but just looking at this concept for the moment. Along with this comes the notion of a local max and a local min, aka relative max and relative min. These are saying the same thing. A relative max is the same as a local max. So local and relative are synonymous here. If we have a critical point, the slope of the tangent line there is 0. It's doing one thing on one side, either increasing or decreasing, and then it's doing the other thing on the other side. Then we would call that a local max. And in an intuitive sense, you can think of this like you're kind of standing on a little hill, and I don't know what's the right word for it. You are sort of master of your domain over this hill here. Now, master of your local domain, right? It could be that you survey your domain and you're pretty impressed. But then when you look farther, you may notice in the background, and I have to draw this quick, otherwise it disappears. So if this gets a little sloppy, that's why, because I got to draw quick. If you, let's say, look in the distance and all of a sudden you see this big hill, well, now you think, shoot, that's not as big as my hill here. However, if you limit yourself to a little local window, you can say that you, like, this value is kind of the highest you can have within this little area. Being honest, I really tend to think of it really like standing on top of a hill. There could be other hills around or mountains, but while you're on that hill, it kind of is still nice. You can still get a better view and that sort of thing. And the reverse of this, where instead of going increasing one side, decreasing, if we go decreasing on the left and then increasing on the right, then we get a local minimum. This is like a little valley. And it doesn't mean you can't reach lower values. It could be that this function, if we kept drawing it, maybe it'll look something kind of like this. So it's possible to go lower. What it's just saying is in this little neighborhood, it's kind of the lowest you can go. All right, now let's kind of put all this together. This is a lot of information, and let's put it all together in one big example. Let's say we want to describe this graph that I've drawn here, and we want to describe it using the language we've been developing over the course of this lesson. So first, let's consider where is it increasing and decreasing. Now that's going to happen where the slopes of the tangent lines to the curve at those points, where those slopes are either positive for increasing or negative for decreasing. Let's first maybe just find increasing. So we're going to be increasing where? Well, if we sort of follow along, here we're decreasing. We get down to, it looks like 3. And then 3, it looks like we get up to, now this is going to be very rough because I drew it by hand. So just kind of bear with me here. It may be slightly off. But let's say it's going to be 3 up until roughly 5. So from 3 until 5, that interval, 3 until 5. Then after that, maybe it looks like it kind of goes down. And let's say roughly from 5.5 up to 7. So also from 5.5 up to 7. To add that interval, we'll go 5.5 to 7. In a similar way, we can look where it's decreasing. And really, you don't even have to get that like fancy intuitively with this. You can just imagine sort of being on a roller coaster, and as you move along to the right, are you dropping down? Well, then you're decreasing. Are you being raised upward or have momentum going upward? Then you're increasing. And that's really it. And certainly, if we go from, let's say, x is equal to 0 down to 3, that's all decreasing. So from 0 to 3. I'll suppose that this ends at the y-axis, just for simplicity. There are other places it decreases, it looks like. So we decrease down here. We increase. Looks kind of like we decrease from roughly, this is just going to be rough, 5 to 5.5. So union 5 to 5.5. And actually, we're going to run out of room here. Let me put decreasing above, because increasing has less space it needs. All right. We decreased from roughly 5 to 5.5. And then it looks like we decrease from 7, let's say, to infinity. We'll say it goes off far to the right in that case. All right, that's for increasing, decreasing. Now, note I went through that a little slow just because, we're learning. But with practice, this goes by pretty quick. Now, local maxima and minima. Another way to read that is, where are the hills and the valleys? The maxima are the hills, and the minima are the valleys. Let's maybe do blue or cyan for maxima. So it looks like there's a little hill here. Let me draw like that, little hill there. Kind of a little hill here. And I think that's about it. So in a local sense, there are maxima, it looks like, when x is equal to 7. And maybe roughly around, actually, what are we calling that? Are we calling that 5? Let's just do 4.5. We don't have to think that hard about it. So maxima at x is equal to 4.5 and x is equal to 7. I won't do minima just for the sake of time and also give you a chance to think through what that would look like. Now the intervals concave up and concave down, kind of finding local minima and maxima are a little bit similar in that regard. You're looking, instead of just hills and valleys, you're looking for concavity. Are you bowl shape up or bowl shape down? Let's use magenta for down, and then we'll use cyan again for up. So it's concave up when you can kind of fit in a bowl shape like this. A bowl shape up, I should say, because there's bowl shape down. If we do that, it looks like it's kind of here to here. Maybe very roughly, we'll call that 0 to 3.5. So concave up goes from 0 to 3.5. Let's see. While we're at it, it looks like we are concave up like there, maybe from 5 to 6. So we'll add on that interval. And then I think after that, it's actually just all concave down. Just to re-stress what that looks like. That's bowl shape down. So we get this. That's from, what do we say? 3.5 up to 5. So we can say concave down is 3.5, oops, to 5. It's also concave down starting here and then continuing to go. So it looks like from 6 to infinity. All right, cool. Now the inflection points are all those points where there's a change from concave up to concave down. Those such points we can just designate here, and we find that here's a spot where we go from concave up to concave down. Here's a spot where we go from concave down to concave up. And here's a spot. I drew those a little dramatically just for effect to make it a little easier to follow visually, but I'll go back and I will tone those down a touch. So we have this, this, and this. Those 3 inflection points, they're going to have coordinates 6 and whatever the function value is at 6. So there's 6. Let's give this function a name. F of x is equal to y. So we have 6 f of 6. That's 1. That's this one here. Then we have this point, which is 5 f of 5. And then I think there was one more, and that looks like it's 3.5 f of 3.5. So 3 inflection points. While we're at it, it's not asked here, but you might ask yourself, just to kind of test your understanding, how many critical points does this thing have? And where are they? Can you go through and find the critical points? If you're so inclined, I might just pause the video and try to do that quick. You don't have to, but it might be helpful. Okay, now the X-intercepts. This current graph, none. The Y-intercept, if we consider it to continue, let's say, right up to this spot, then that would be our Y-intercept. Maybe we'll call that B. Or if we wanted to, maybe we'll put it as a point, 0B. Yeah, let's just put both. Undefined points, in this case, there wouldn't be really any undefined points. That would be where you have asymptotes, would be one particular case. Or if you have like a hole in a function, that sort of thing. I should have said find the critical points, because there could be more than one. Okay, I think that is it. Hopefully this was educational. That would be great. And remember, we will see you in class on Monday. Have a good day.